Electron gain enthalpy is the energy released in kilojoule of 1 mole of gaseous atom while it accepts an electron to form an anion. The process of gaining an electron may be endothermic or exothermic. That is, if an electron is added up to the outer shell of an atom spontaneously, then energy is released and the process is exothermic and electron gain enthalpy is negative. The magnitude of the negative electron gain enthalpy increases with the ease with which the electron is added. Or in other words, if the electron is added to the atom more easily, then the magnitude of the negative electron gain enthalpy increases. And if the electron is added up more reluctantly, then the magnitude of the negative electron gain enthalpy decreases. In some atoms, this reluctance is so much so that the electron gain enthalpy becomes positive and the process becomes endothermic. In that case, no energy is released. Rather, energy is required to be supplied in order to achieve an electron. Now, the electron gain enthalpy depends on factors like the charge on the nucleus, the atomic size, symmetry of electronic configuration. The d-block transition elements have a more complicated chemistry to be understood under the same reasoning. So, for the time being, I am hiding this part. As charge on the nucleus increases, it can attract the added electron more and hence electron gain enthalpy become more negative. There is an exception in group 2, group 13, group 15 and group 18. See here that the nuclear charge increases across a period, so do the electron gain enthalpy. For group 13 over here, the shielding is due to both 1s and 2s electron, whereas in group 1 there is shielding due to 1s electron only. In case of group 2, group 15 and group 18, this factor comes into play. Down the group also, the nuclear charge increase, but here the electron gain enthalpy decrease. Why? This is because of the atomic size. As the atomic size increases, the pull on the added electron becomes less and the value of the electron gain enthalpy becomes less negative. This atomic size factor is dominant while we move down the group, with some exceptions in the second period. This is because the electron to be accommodated goes to the 2p orbital, which has less space than 3p orbital, and therefore offer greater repulsive force from the already existing electrons in the 2p level. Now the last factor, that is symmetry of electronic configuration, is perhaps a factor which can nullify the effect of the other two factors. I am also revealing the transition elements now. A symmetry in electronic configuration that has fully filled or half-filled outer degenerate orbital leads to that extra stability which will make the process of gaining an electron endothermic. Or in other words, symmetry in electronic configuration lead to positive electron gain enthalpy. The atoms that have symmetric electronic configuration in the periodic table of elements are the noble gases. Among the noble gases, helium has the lowest positive value due to least atomic size, and neon has the highest positive value due to absence of unoccupied orbital. Then comes the group 2 elements. Beryllium and magnesium has positive electron gain enthalpy due to symmetry in electronic configuration. These elements also have symmetry but have empty orbital with more and more space. Therefore, the electron gain enthalpy becomes slightly negative. Then comes the group 7 elements. This element over here is manganese, which has a half-filled 3d orbital. The 3d orbital, being smaller in size than 4d and 5d over here, has a great enough exchange energy of the exactly half-filled 3d orbital that spontaneous addition of electron becomes impossible. So it has a positive electron gain enthalpy. Here the exchange energy of the exactly half-filled 4d orbital is not so much high. So the reluctance to electron addition eases out and the electron gain enthalpy becomes negative. Here it is less negative because a whole set of 4f orbital electron offer shielding as well as repelling effect on the added electron. Then comes the group 12 elements. These three elements have symmetric electronic configuration with fully filled orbital, so they have positive electron gain enthalpy. Then comes the group 15 elements. Nitrogen over here has positive electron gain enthalpy due to symmetry in 2p half-filled orbital and the absence of unoccupied orbital. These elements have unoccupied orbital and therefore cancel the effect of symmetry and hence have negative electron gain enthalpy. Here, hafnium also have a positive electron gain enthalpy, probably due to the fact that addition of an electron in the 5d orbital is resisted by the shielding effect offered by a full set of 4f orbitals. This is sometimes called the first electron gain enthalpy because there is always a scope for gaining a second electron of a -1 ion to form a -2 ion. In that case, it will be called the second electron gain enthalpy. The second electron gain enthalpy is always positive because it becomes difficult to add an electron to an anion of -1 charge.